Hello. We're going to discuss a problem that involves the image of the union and intersections, and then the union and intersections of images. So we have the proposition here. What I want you to notice is that you have an equality here, but you don't here. So what's the problem? Let's prove the first statement. In order to prove that two sets are equal, you usually prove two directions. The left side is a subset of the right side, and the right side is a subset of the left side. So let's do that. We show f of C union with D is a subset of f of C union with f of D. So we start with for every y in f of the union of C and D. Usually we use y for the image and x for the pre-image. That's just convention. It doesn't really matter though. All right, so what does it mean? It means y is the image of C and union with D. That means there exists some element x in C union with D such that f of C, f of x equals y. That's what this statement means. All right, so then we have x in C union with D, though x should be in C or D. So x is in C or x is in D, such that you have f of x equals y. And you have two situations, right? So if x is in C and f of x equals y, now that shows y is in f of C, is in f of C. All right, so y is in the right side, right? It's the right side. Okay, so that shows the subset for this case. For this particular case, f of C union with D is a subset of f of C union with f of D. And on the other part, if x is in D and f of x equals y, then you would have y is in f of D, then you have the same result. So both cases would give you a subset, okay, of the left side, a subset of the right side. So we have shown that it's this direction. All right, let's look at the second direction, the other direction. You want to show that f of C union with D is a superset of f of C union with f of D. And you start with the right side. So for every y in f of C union with f of D. Then you would say, well, y has to be in f of C or y is in f of D. And then you show for each case, this one, obviously y is in f of C union with D. And this one obviously also shows y is in f of C union with D. So both cases will tell you y is in the right side. So that shows this direction. We have two directions. We show the equality. All right, so let's look at the second statement. We do the similar thing. For every y is in the left side, and now we can conclude that there exists x in C intersect with D such that f of x equals y. Okay, now you see x is in C and x is in D. So X is in C, you would conclude that Y is in f of C. Okay, so Y is in f of C. And when X is in D, you have Y is in f of D, but it's AND. So both have to hold, and you have shown that Y is in f of C intersect with f of D. Okay, so that shows this statement. Now, why you cannot have equality? Equality doesn't work. Okay, I'll give you an example, very simple example. So f is R to R, okay, and f of x equals x squared. And you let C to be a set, which is 1. D is another set, -1. Then C intersect with D is empty. So f of C intersect with D is empty. Now, f of C is what? Is 1. Sorry, f of C is this set. It's a set, not value. Okay, f of 1 is 1, and f of D is also the set of with an element 1. So actually, f of C intersects of f of D is the set of value 1, and these two are not the same. Okay, so that shows equality doesn't work doesn't hold for this these two sets. Okay, so the problem here is that when you try to show the right side, you try, okay, which is you cannot show. You want to show that the right side is a subset of the left side. So you start with Y is in f of C intersect with f of D. Okay, so that you can conclude that Y is in f of C. That's no problem, and Y is in f of D. Okay, so that means there exists some value x in C such that f of x equals Y. Now look at that one. Well, there does exist an element in D, but not necessarily this x. Maybe different x. So you have to sort of write some x prime here. There exists x prime possibly equal to x, possibly not. So there exists x prime in D such that f of x prime equals Y. But then it's not necessary that x and x prime to be the same. So these elements, well, may not be in the intersection. There may not have any element in the intersection that make fx to be y. Okay, so that's a problem. The problem comes from the 1-to-1 condition. So if f is 1-to-1, then you do have an equality. Okay, so there's another proposition if you want to say. So if f is 1-to-1 injection, okay, 1-to-1, then you have this equality. Okay, f of C intersect with D would be the same as f of C intersect with f of D, because you have 1-to-1 condition. You have x and x prime in previous example, but because it's 1-to-1, x prime has to be the same as x. All right, then you there exists x in the intersection, and that shows the other side. To make the comparison, we have another proposition, which is the inverse of the image of the union and the intersection versus the union and intersection of the inverse images. And we do have both equalities. Okay, so the proof is very similar, and I guess I'm gonna just neglect it. Okay, that's for it. Bye-bye.